Hello, my name is Landon Kehr, and I'm a senior undergraduate student at Taylor University in Upland, Indiana. I'm going to be talking about my summer research project as part of the iComp Bio REU program at the University of Tennessee at Chattanooga. My project involves addressing sample biases in genome-wide association studies for SARS-CoV-2. Before we begin, I'd like to take a minute to thank my mentor, Dr. Ziwei Ma, the program director, Dr. Hong Chin, and the rest of the iComp Bio REU program at the University of Tennessee at Chattanooga for their support, as well as the NSF for their financial support. A little bit of background info on the pandemic. The COVID-19 pandemic is caused by the novel coronavirus SARS-CoV-2, which stands for Severe Acute Respiratory Syndrome Coronavirus 2. It is a part of the same family of viruses as the SARS virus, which caused the original SARS pandemic in 2003. As of the date of this recording, in July of 2021, there have been over 192 million confirmed cases, resulting in over 4 million deaths as a result of this pandemic. The SARS-CoV-2 virus has a genome that contains over 30,000 base pairs, which is one of the largest genomes we've ever seen in a virus that infects humans. The nature of this virus also causes it to mutate rapidly, resulting in many different variants that have slightly different characteristics. Many of these mutations are caused by single nucleotide polymorphisms, or SNPs, which is when one nucleotide in the genome is replaced by a different one. Some research has shown that certain mutated strains of this virus are correlated with an increase in transmission and mortality rates of the disease. This is why it's very important that we continue our research into these variants into the future. We can classify these variants according to what we call clades. Since the beginning of this pandemic, we have developed and used many different systems of classification of clades, as you can see in this chart. When the virus mutates, it often contains many different SNPs all throughout the genome. Some of these groups of SNPs are able to survive and thrive better than others due to natural selection. When a group of SNPs differs widely from other groups, we can classify it as a new clade. My research focuses on the GISAID system of classification, as you can see on the right here. Through the process of collecting data for COVID-19, there have been many potential sources of bias that have been documented. For example, the proportion of positive tests to sequence tests in a country can vary widely from country to country. Specifically, countries like the UK that have lower numbers of total positive tests, but a higher percentage of sequence tests, can differ from countries like the United States that have a higher number of positive tests, fewer of which are being sequenced. Many different factors, specifically economic, cultural, and environmental, can have an effect on who is getting tested at what times in different countries. And these can also create biases in our data set. My project involves using statistical techniques of undersampling and oversampling to try and reduce these biases. Using our software, I created random undersamples of 20 and 40 cases and random oversamples of 200 and 500 cases from each country in my data set. These oversamples were done with replacement, while the undersamples were done without replacement. My data comes from GISAID, which is the Global Initiative on Sharing Avian Influenza Data. GISAID was started in 2008 with the goal of allowing up-to-date public access to data from countries all over the world to be shared among each other. It has been used extensively throughout the H1N1, H7N9, and now the COVID-19 pandemics. As of today, there have been 9 individual clades of COVID-19 variants that have been classified by GISAID. These are the G, the GH, the GR, the GRY, the GV, the L, the O, the S, and the V clades. These clades are named for certain genetic markers that are present in many of the variants inside the clades. My data set originally contained over 1.4 million samples from 175 different countries. I then condensed this down to only include data from the 120 countries that produced at least 50 samples. The tests were collected between April of 2020 and May of 2021, and the test dates were then rounded for the purpose of categorization into weeks and months. This is an example of some of the data points I was using. We can see here the clade that the sample virus was a part of, the country of the test, the continent of the test, as well as the date that the test was collected. After all this cleaning, we still have almost 1.4 million data points. I then created a histogram to reflect the total count of each clade for the original data set and for each of the resampled data sets. These are the undersample of 20, the undersample of 40, the oversample of 200, and the oversample of 500. And as we can see in all 4 of these resamples, the L, the O, the S, and the V clades are much higher represented than they are in the original data set. I then broke the data down into month and week categories. For the month categories, month 1 represents April of 2020, and month 14 represents May of 2021, only through May 7th, because that's when the data set ended. We can see in the original data set, as well as each of the resampled data sets, the undersample of 20, the undersample of 40, the oversample of 200, and the oversample of 500, that certain clades become more frequent or less frequent over time. However, one main difference I see in this data is that in the original data set, clades such as the L, O, S, and V clades that are much lower represented at the beginning slowly fade out over time and become basically non-existent towards the end. While as in the resamples, 20, 40, 200, and 500, we can still see all of these clades represented throughout the entire span of data. So these resamples appear to give more weight to the clades that are less represented in the original data set. I also broke down the data into weeks, with week 1 representing the first week of April 2020, and week 58 on the end representing the first week of May 2021 when the data set ended. So we have the undersample of 20, the undersample of 40, the oversample of 200, and the oversample of 500. Again, just like with the month data, you can see over time in the original data set, certain clades are almost disappearing throughout the world in terms of their frequency. While as in the resampled data, the frequency of these clades is still apparent throughout all of previous year. One main difference I see in the plots based on week compared to the plots based on month is the variation from week to week, especially in the resampled data sets. For example, the G clade up here has a much smaller percentage in these couple weeks before jumping up to almost 50% of all of the data in the following week. and then immediately going back to about 10%. This variation is not apparent in the samples distributed by months. This could be caused by smaller sample sizes in certain weeks compared to other weeks. Next, I broke down the frequency of clades according to continent and country that the tests were a part of. So here we have the original data broken down into continents, as well as the undersample of 20, the undersample of 40, the oversample of 200, and the oversample of 500. I did this to try and determine which clades were more common in which parts of the world. Again, we have significant differences appearing between the original data and the resampled data. Some examples of this are in the North American continent. We see over half of the data is represented by the GH clade in the original data set, while as in the resampled data, it is closer to a quarter of all of the data as a part of the GH clade. We see many different differences between these resamples and the original data set. And again, we see these underrepresented clades L, O, S, and V being more represented in the resampled data than in the original data. I also broke down the data set according to which country the test came from. This is a bit difficult to read, but I kind of ran out of time in my summer project to create a better diagram of this distribution. So some future work that would be beneficial in my eyes would be to create a world map with all of the countries and overlaying each of these pie charts over their specific country to better determine how the original data differs from the resampled data of 20, undersample of 40, oversample of 200, and oversample of 500 in terms of country. The location data is interesting to me because it can give us insight into why certain clades are more prevalent in some continents and countries versus other continents and countries that might have different climates. So some of the temperature data and the humidity could have an effect on why certain clades are more prevalent in some areas versus others. I wanted to determine how significant these differences between the original sample and the resamples was statistically. In order to do this, I used Pearson chi-squared tests of homogeneity. I did this because it's a relatively simple test that will easily let us know if the differences are significant. I used a significance level of a p-value of 0.05, which is represented by these black lines on the graph. This is also a logarithmic scale. So this is, in fact, the p-value of 0.05, meaning any data point above this line is statistically significant, while any data point below this line is not statistically significant. I also broke up the data into continent and viewed it over weeks and months. So the results of this between the undersamples and the oversamples with the weeks and months. With the weeks, there are a lot of data points and a very cluttered graph that is kind of hard to read. And it is the same through all of the resampling. And oversample of 500. And this could be due to differences in sample sizes from week to week, just like with the total frequency plots earlier. However, when I broke it down into months, it became much more easier to read, as well as giving us a better picture of which continents in which months had statistically significant differences between the original data set and the resample data set. So for the undersample of 20 data set, it looks to be about half and half, with half of the months and continents representing statistically significant differences, while the undersample of 40 appears to be about the same, maybe a few more data points being statistically significant. But the real interesting parts are the oversample of 200 and the oversample of 500, with almost all of the data points in both representing statistically significant differences over month and continent between the oversamples and the original data set. And this could be also because of the larger sample sizes in the oversamples compared to the undersamples, which may not have been statistically significant enough with smaller sample sizes to show a statistically significant difference. So in conclusion, there is some future work to be done here, like I said, with the country map to better represent the clade frequencies compared to these pie charts, which are kind of small and difficult to read. So that would give a better representation of the specific frequencies over country. And another thing would be to incorporate geographic weather data to determine if such factors as humidity and temperature could cause more certain clades to become more dominant in certain areas, and then continuing that into whether or not those clades have a higher transmission or morbidity compared to the other clades that maybe aren't as prevalent in those areas. If you want to learn more about this subject, I recommend going to the GISAID website or the Next Strain website, both of which have many interactive diagrams that can help you learn about this topic. And here's the abstract for this presentation, as well as my references. Thank you.